We now want to compute estimators. So in order to apply the results which we have learned to real-life applications, we need estimators of mean and variance. So often what happens is that we have a sample. So say you have a sample of stock prices. So say this is stock price of some corporation, say ABC Corporation. But we have no idea of what the underlying distribution of this stock price is. So if you knew what the underlying distribution of the stock price is, then mean was very easy to calculate. So mean is nothing but expected value of this particular stock price, which you know you can compute from minus infinity to infinity using this result. So, but this result which we have studied obviously requires you to know this f of x, which is nothing but the density function. And you can again obtain this density function after differentiating the distribution function. But what I'm trying to say is you have no idea of what this is. So we do not know what the underlying distribution or the density function of the stock is. So how do we now compute mean and variance? So for that purpose, we need estimators of mean and variance. So first thing you do is you have a large enough sample. So from this sample, you find the sum of all this random variables, and then you take the average. Sn by n gives you average. So we are saying that this average is the estimator of mean. That is, this is approximately equal to mean, or which is equal to expectation of xi. So rather than integrating it, you could just take the average and still find the mean. Second is variance. So this s square, which is equal to 1 over n minus 1 summation I equals to 1 to n xi minus x bar. This x bar is plugged in here, and this xi is all these x1, x2, x3 all the way to xn. Now this is the estimator for variance, sigma square. That is variance of this random variable xi. So this sigma square is nothing but variance of the random variable xi, and this random variable xi is drawn from the distribution function. Say, now again as before, it is drawn from this distribution function, but you have no idea of what this distribution function is. You just know it is drawn from some distribution function, but you have no idea. So notice the beauty that we have been able to estimate. So this is estimate of variance, and this is estimate of mean, without knowing what the distribution function is. So why is this an estimator? Because we will now show that expectation of x bar is mu, expectation of s square is sigma square, and that's why we call this as estimators. Note, x bar and s square are themselves random variables. You have no idea, or we are not worried about what the distribution of x bar is. We are not worried about distribution of s square. Notice x bar itself is made up of random variables x1, x2, x3 all the way to xn. Similarly, s bar square is also made up of random variables x1, x2, x3 and so on. So this is a random variable, this is a random variable, but the expectation of this random variable is the mean of this distribution, and expected value of this random variable is the variance of this distribution. Now x bar is an estimator of mu. We have already shown in the previous lectures that expected value of Sn by n, so Sn by n is x bar, is mu. And now we need to show this condition. Expected value of x square is sigma square. So in the previous lecture we have shown that variance of x bar is sigma square by n. So sigma square by n we have already shown is equal to expected value of you can say x minus x bar minus expectation of x bar, and then you have to square this term. So this is the definition of variance, but expectation of x bars is nothing but mu. So here expectation of x bar is mu. This we are writing it right here, so you can put mu here. So you have mu here. So now first I'm going to rewrite this formula. So rewrite it as n minus 1 s square. So this is equal to, you sum it up from you just copy this formula right here, you add minus mu and plus minus mu, both of these cancel out. So this and this cancel out. Again you can rewrite this as xi minus mu minus x bar minus mu, and then you square it. So the first term is xi minus mu square here, plus x bar minus mu square, and then minus 2 x bar minus mu and xi minus mu, and then you take the summation side and side. So this is summation of the first term, summation of the second term. Notice that this x bar does not depend upon I. So x bar is just, you have already taken sum of all the variables, so it is independent of this indices under here. So this I summation has no impact on x bar. So this is a constant, and therefore this you can rewrite as, say, n times x bar minus mu square, because you are summing it n times. I goes from 1 to n. So this is kind of a constant. Similarly, x bar minus mu is a constant, it comes out. Now what about this term? Now if you sum this term, obviously you take it, take the sum of xi and mu. So if you sum all the xi's, what you get is Sn. But Sn is equal to n times x bar. So summation of all xi is Sn, and Sn is n times x bar. So for this term, let me write this in a different color. So for this term, this is equal to n times x bar minus n times mu. So when you multiply this all out, this becomes minus 2n times x bar minus mu square. So you add this and this term, you get minus n x bar minus mu square, and this first term you just copy it as such. Now you take expectations of both sides. N minus 1 is a constant, it comes out. So expectation of s square is equal to, so this summation, expectation sign comes inside the summation, minus n times x bar minus mu square. So n is a constant, comes out. Now notice this term. Now this term is precisely this term right here, which is variance of x bar. So this becomes n times, so instead of this I write n times variance of x bar. But expectation of xi minus mu square, this is nothing but, you can rewrite it as expectation of xi minus expectation of xi square, because mu is your mean. So this expectation of xi is the mean, because we are drawing xi from the same population, this distribution function. So this is n times sigma square, because this is the variance of the population. So notice that variance of x bar is sigma square by n. So here you can write sigma square by n. This is n cancels out, so you have n sigma square minus sigma square, which is n minus 1 sigma square. Now this n minus 1 will cancel out with this n minus 1. So you have expected value of s square is sigma square. So now we have estimators for mean and variance. So we can talk about quantitative trading strategies.